how could we get all of this messy data to collapse? And so we were struggling for kind of what's the underlying physics, and hence what might be the important parameters. And one of the assumptions that we needed to make in order to get an underlying model that would get this data to collapse was that notion that only similar sized particles can collide. And we ended up getting this. And I know it still has some scatter in it, but all the data is now converging much more closely onto one line. And it means that that one blue line is actually a pretty decent predictor of all of the data over a range of raw water turbidities, a range of coagulant dosages, and a range of residence times in the flocculator. And this is exciting to me because this is the very first time that there's been a model that describes flocculation. So that's pretty cool. We actually have a model and we can begin to think about that in design. So instead of having this mess of data all over the place, we now have it at least beginning to converge on one line. This is the equation, the underlying modeled equation that was used to create that beautiful blue line in the previous graph. And this is what goes into it. So G is a velocity gradient. That's the deformation of the fluid, the rate at which the fluid is being deformed. T is time in the flocculator. Lambda, the capital lambda, is particle spacing. So lambda without any subscript is the final spacing between particles, and lambda 0 is the initial spacing between particles. So if you have a really turbid or really dirty suspension, lambda is small. The spacing between particles is small. And when you have a really clean suspension, the spacing between the particles is large, lambda is large. So from a treatment perspective, what you're trying to do is create a large lambda, i.e. a suspension without many particles. We used lambda because that was like the parameter that was important in the model. It was actually the spacing between the particles. Then alpha is the efficiency of attachment, and the question about whether or not two particles actually remain attached when they hit is a function of the amount of the surface that is covered with the coagulant. The diameter of the core particle is d sub Cp, and the core particle is like the starting particle of clay or cryptosporidium, and maybe some coagulant nanoparticles attached to it. That is the particle that is then going to stick to other particles and form a flock. And K is a rate constant. It's dimensionless, and it includes information on size distribution, and it is currently our fitting factor for this model. It means that we're guessing at that one, or we're fitting that to the data. So that's like the 1 degree of freedom that we have in this model to fit the data to the curves. So that's the model, and what pops out is that GT is an important parameter. And indeed, GT is what has been used to design flocculators for a very long time. So we're not the first ones to use that. And I thought it'd be helpful to show, like, what in the world, what does GT mean? So G is du dy. It's the change in velocity over distance. And if you want, you could integrate that velocity from 0 to lambda, which is the separation distance between two particles. And you could integrate that over from 0 to VR, where VR is the relative velocity between those two particles. And what you get is that lambda times G is equal to the relative velocity between those two particles, so that given the spacing between two particles, lambda times g is the relative velocity that those two particles will have. That'll be the velocity that they're approaching each other at, or passing by each other at. And you can also think about, well, how far have these two particles moved as a function of time, given their relative velocity, given how far apart they are? And that's L deformation. So GT can be thought of, GT is dimensionless. So you could think about it maybe many different ways, but the easy way that I'm proposing is think about it as the distance that two particles travel relative to each other as divided by how far apart they are. So in Avocado, we use a GT for designing our flocculators of 37,000. That number means that if two particles had a separation distance of 1 millimeter, by the time they've moved through the flocculator, they have moved relative to each other a distance of 1 millimeter times 37,000 is equal to 37 meters. Is that kind of phenomenal? So that motion is just because we caused the fluid to deform. And that's why they move so far. And it is that motion of 37 meters based on a separation distance of 1 millimeter that is causing particles to collide with each other. Okay, so that's what we're doing with this GT, is we're deforming the fluid a lot. GT is a measure of the total deformation of the fluid that we create in the flocculator. Okay, so enough of that. And I'm going to skip some slides because there's just too much to talk about. But here's the next important concept, and that is, in addition to there being some particles that we'd like to stick together and the coagulant nanoparticle that we dose to make them sticky, there's also dissolved organics in the water. And dissolved organics have a huge impact on how flocculation proceeds. And so we can't just ignore this. So coagulant nanoparticles are sticky. Natural organic matter is not sticky. And so and the natural organic matter will happily stick to the coagulant nanoparticles. And so we get this little blob that I have there on the right. And if we take two of those and we try to get them to stick together, if the point of contact is a dissolved organic molecule, they won't stick because that dissolved organic molecule isn't sticky. So this means that if we take these clay particles that we're coating with coagulant nanoparticles, and those might not stick because they don't hit at a place where there's a coagulant nanoparticle. But when we add these coagulant nanoparticles that are themselves coated with dissolved organic matter, they don't stick to each other. And that means that if we take two clay particles and the clay particles are coated with coagulant nanoparticles and the coagulant nanoparticles are coated with dissolved organic matter, now when we bring those two together, even though we might have hit where there was a coagulant nanoparticle, it still doesn't stick because the coagulant nanoparticle was covered with dissolved organic matter. Okay, so if you want to think about this a completely different way, if you think of your sticky note, your little memo pad, your little sticky note as the coagulant nanoparticles are on that sticky part. And then if you take that sticky note and you dip it in sugar and then try to attach it to your desk, it's not going to stick. And it's because that sugar has coated the stickiness of the sticky note. The same thing is happening in water treatment. Our coagulant is being coated with dissolved organic matter. So this is what happens. we ran the experiments, and another one of my students, Ingda, ran these experiments, and she collected lots of data again, and she discovered that, or we discovered that we could model this effect too, and it's just geometry. It's the geometry of how much of a coagulant nanoparticle is covered by each dissolved organic molecule. And based on that, you can figure out how much coagulant you have to add before you start having any coagulant that's actually not coated with the dissolved organic matter. So if we look at this plot, actually, I'm going to pass on describing the plot. I'm going to go right to the concept. The concept is that when you add the coagulant, the dissolved organic molecules, because of diffusion, they very quickly attach to the coagulant nanoparticles. And if you keep on adding more coagulant nanoparticles, all of the dissolved organic matter eventually is tied up on those coagulant nanoparticles. And then you keep on adding more coagulant, and then and only then do you start having some coagulant that isn't coated with the dissolved organic molecules. And only then do you start having stickiness and flocculation start to happen. So to completely contrast this, if you start with, okay, now let's look at the brown curve. The brown curve here is this last one where there was a lot of humic acid. HA is humic acid. So there was lots of humic acid. And what you see is that this X, when the Y axis is equal to 0, it means no removal. And a 1 on this means 90% removal. So there was no removal until the coagulant dose was greater than 1 milligram per liter. So it wasn't until you had already added 1 milligram per liter of aluminum that finally there was enough coagulant present so that there was a little bit of naked coagulant that was still sticky available to begin attaching to clay particles and then begin to attach those clay particles to each other. There's a couple sections of, a couple slides about how you can actually calculate how much of these particles are coated with sticky surfaces, like what the fraction of sticky surfaces is. It's geometry and probability. I don't want to go into the details, but I want you to know that this is all part of the model, and it's relatively simple ideas of geometry and probabilities. And then this is the performance curve taking all of Ing Da's data, where she was doing coagulation of humic acid plus clay, dissolved organic matter plus clay, and showing that that all nicely falls onto one curve as well. So this is the Moody diagram concept, that by having the right x-axes and y-axes, it converges onto one single curve, which means that we now have a model that describes that process of flocculation of inorganic particles and some dissolved organics. Okay,